Hello. Hello, dear student. Welcome to Q Physics Academy. So, we are already start B.Sc Mathematical Physics major course for university levels. Basically, this course is for those students who are in B.Sc 4-year B.Sc honors and research course in semester 4. Okay, you already know. I hope your semester 3 exams, some university have a semester exam will now continue, and some university already has already done. So basically this course is for those students who are in semester 4. Okay, in semester 4 there are many topics basically included in lectures 1. I had discussed about that, right? So now this is the lecture number 2 of complex analysis, right? So in the lecture number 1 we'll discuss many topics, right? This is the De Morgan's theorems, and also what are the complex numbers and how to represent graphically the complex number, etc. So this is the lecture 2. Lecture 2 we discuss some important principles of complex analysis. Okay, so let's this is the lecture 2. Okay, let's start this video. So those students who are new in my channels, please subscribe my channel and like the video also, and share with friends who are in BSc Physics honors course in semester 4. Okay, so next we'll discuss here the complex numbers. So let's try to find out a root of complex number. How can I find out the root of complex numbers actually? Okay, so topics is basically root of complex number. Root of complex number. Okay, so we already know. Let's say a complex number of let's say complex number, let W be a complex number okay. So a complex number can be written as a, that is like a x plus iy, and that is equals to written as w equals to z. So this is a complex number. Okay, you already know. Let us consider this complex number have nth root. Okay, let again consider omega is an nth order complex number. That is nth root of a complex number. Nth root of a complex number. Okay, so then w to the power n equals to z, and that is equals to w equals to basically z to the power 1 by n, where n is a positive number. Just focus where n is a positive number. Okay, so when a complex number have a nth root, it's a represented or written is like that. So this is equation number 1 and this is equation number 2. Okay, let's try to find out how can I write z to the power 1 by n. Okay, so we already know, so that is w equals to z to the power 1 by n. So z to the power 1 by n can be written as z equals to r e to the power I theta whole to the power 1 by n. This is represent z in the plane polar coordinate systems, right? So z can be written as one is Cartesian coordinate system x plus iy, and also this Cartesian coordinate systems have a relations with plane polar coordinate system. X equals to r cos theta, y equals to r sin theta, right? So using the connection between Cartesian and polar coordinate system, we can write a complex number in polar coordinate system that is equals to r equals to the power I theta. Now using the de Moivre's theorem, that is a to the power I theta, using de Moivre's theorem, e to the power I theta equals to cos theta plus I sin theta. Okay, let's substitute this value, that is equals to r cos theta plus I sin theta whole to the power 1 by n. Okay, so that is equals to r to the power 1 by n. It is very simple. Next is equals to cos theta plus I sin theta whole to the power 1 by n. Now the main concern is how can you write this, the second part, basically cos theta plus I sin theta part. Okay, cos theta plus I sin theta part. So that is again a very important rules actually. Okay, no, sorry, this is not a de Moivre's theorem. That is basically Euler's formula. I'm sorry, this is basically Euler's formula, using the Euler's formula. This is, I'm sorry. Okay, this is basically Euler's formula. Yes. Okay, Euler's formula. Now we apply here the de Moivre's theorem, that is nothing but z to the power n is equals to r to the power n cos n theta plus I sin n theta, right? So now apply this case here. So that is equals to r to the power n is equals to cos theta plus 2 pi k upon n plus I sin theta plus 2 pi k upon n. So where k is nothing but 0, 1, 2, 3 up to n minus 1. Okay, so from which we get n different value for z to the power 1 by n. Okay, for n different value, because for k equals to 0, k equals to 1, k equals to 3, etc, etc. So that in the way we can find out the root of any complex number. So okay, so this is the equation number 3. So from equation 3, we get n different values of z to the power 1 by n. That is nothing but the n different root of z. N different root of z. Okay, I think I understand what I'm trying to say. Okay, fine. Okay, let's trying to understand using some example. Okay, so let's say this is the example 1. Find out the cube roots of a complex number. Find out cubic roots of a complex number, that is z cube equals to 1. Okay, it's time to find out the z cube equals to 1. So how can I find out z cube equals to 1, the cube roots of z? Okay, so now here that is basically z cube equals to 1. Now we're trying to write 1 in polar coordinate system. So where let's 1 can be written in polar coordinate system. Okay, so that is equals to e to the power I 2 pi for one root. Okay, e to the power I 2 pi is basically it gives one root, but here z have a 3 roots, so you can here written here the k have a different value 1 2 3. Okay, k have a different value here, so k is basically 0 1 2 3 minus 1, it's means 0 1 2. I think you understand why in the theory part we introduce the k value actually here. Understood? So if you write here e to the power I 2 pi, then it gives you plus 1. Don't worry about that. But the complex number is basically z cube equals to 1. So it gives you 3 roots of z complex number. That's why we introduce the k here actually, and k have a value 0 to n minus 1. N is the number of root of this complex number actually. Okay, I had already discussed about that. Okay, very good. Now okay, so z cube is equals to a to the power I 2 pi k. Okay, understood? 2 pi k. So z is equals to a to the power I 2 pi k upon 3. Okay, so now substitute each value of k. So substitute each value of k, that is 0 1 2, basically 3 values k. So when k equals to 0, then z equals to z equals to e to the power 0, right? So it gives you its roots equals to 1. So the root is one root is z equals to 1. When k equals to 1, then z equals to e to the power I 2 pi upon 3. So that is equals to cos 2 pi upon 3 plus I sin 2 pi upon 3. So cos 2 pi by 3 is gives you value minus plus I sin 2 pi by 3 gives you root 3 by 2. So this is the another root of this complex number, that is equals to sorry, minus of plus I root 3 by 2. Okay, this is the second root of this complex number. Again, when k equals to 2, then z equals to e to the power I 4 pi upon 3. So it is equals to basically cos 4 pi by 3 plus I sin 4 pi by 3. So cos 4 pi by 3, it's again minus up, or sin 4 pi by 3 equals to minus, so plus minus minus I root 3 by 2. So the roots are of this complex number. So the roots of the complex number each z equals to 1 minus half plus minus I root 3 by 2. Okay, so this is the way you can calculate the root of any complex number. Okay, let's take another problems. Okay, another example of to find out the complex number, that is example 2. Okay, find all roots of complex number z for which z to the power 5 equals to minus 32. So for this complex number we get 5 roots actually, right? This is a simple and first solutions arise in your minds actually. Okay, so okay, this is the complex number z to the power 5 equals to complex equations. Okay, z to the power 5 equals to minus 32. Okay, so this gives you basically 5 roots. This is the okay. So basically in, so for n have 5 values for different in 5 different n values. We get the roots of the z complex number. Okay, very good. Next, how can I find out the solutions? Just look here. So you given in your questions given z to the power 5 equals to minus 32. Don't worry, we can write this is equals to 32 into minus 1. Okay, so we are already discussed in the previous questions 1 can be written as e to the power I 2 pi k have a value 0 1 up to n minus 1. All right, so minus 1 can be written as e to the power I pi, e to the power I pi plus 2k I plus I plus 2 pi k I pi plus 2 pi k, and here also k is nothing but 0 1 up to n minus n. So 1 can be written as e to the power I 2 pi k, minus 1 can be written as e to the power I pi plus 2 pi k. Okay, very good. Okay, so z to the power 5 is equals to 32 and e to the power I pi plus 2 pi k, and k have a value 0 1 2 3 and 4, right? So these are 4 values actually. Okay, so put here k equals to 0 1 2 3 4. Understood? Very good. Now apply here the De Moivre's theorems. So that is equals to z 32 e to the power I pi plus 2 pi k whole to the power 1 by 5. So it is equals to 32 whole to the power 1 by 5. So e to the power pi plus 2 pi k upon 5, where k is equals to 0 1 2 3 up to 4. Okay, very good. So this is the complex number. Now we can find out the root for different k values, right? This is the very simple case. Okay, so okay, let's simplify this. This is equals to 2 to the power 5, that is equals to 1 by 5. So e to the power I pi plus 2 pi k upon 5, and k equals to 0, 1, 2, 3, 4. So this is equals to 2 e to the power I pi plus 2 pi k whole to the power 5, and k equals to 0, 1, 2, 3 and 4. Understood? So this is the complex number. So now find out the roots of this complex number. So when k equals to 0, then z equals to 2 e to the power I pi by 5, right? So yes, this is the first root. You can find out the e to the power I pi by value when k equals to 1, z equals to 2 e to the power 3 pi by e to the power I 3 pi by 5, when k equals to 2, z equals to 5, yes, z equals to 2, yes, 2 e to the power I 5 pi by 5, that is equals to 2 e to the power I pi, and that is equals to minus 2. E to the power I pi is equals to minus 2. Yes, k equals to 3, z equals to 2 e to the power I 7 pi upon 5, and k equals to 4, z equals to 2 e to the power I 9 pi upon 5. So these those fives all are the roots of this complex number. Okay, so this is the way you can calculate the roots of any complex numbers actually. I hope you understand the techniques we follow, the methodology here follow to solve the roots of any complex number. Okay, very good. So okay, let's fine. Next, take another topic, that is basically complex variable. Okay, let's move on to the complex variable. So what is complex variable? भाई तुम लोग एक बात आराम से जान लो, ठीक है? बेसिकली जो इधर हम लोग जो पढ़ाई कर रहे हैं अच्छे से, ये हम लोग एकदम डिटेल स्टडी कर रहे हैं अच्छे से. तुम लोग एक एक टॉपिक को अच्छे से देखो, ठीक है? एक एक टॉपिक को अच्छे से नोट डाउन करो. एक एक टॉपिक को अच्छे से नोट डाउन करने के बाद प्रीवियस ईयर तुम लोग लगा लो, देखना अच्छे से तुम लोग सॉल्व कर पाओगे प्रॉब्लम को, ठीक है? तो एक एक प्रॉब्लम का सल्यूशंस मैं तो मतलब हर एक प्रॉब्लम का सल्यूशंस मैं नहीं करा सकता एक्चुअली. यस, I don't give you the proper solutions of each questions, but I give you the solutions of maximum questions. Okay, so in the channels I give you the theory as well as some problem solutions of IIT JAM and just also CS and NET and CS and NET GATE. But few questions I covered, only few questions, but your responsibility is to finish your whole free IQ and along with the some specific some say special problems also from your standard textbooks. Okay, understood? I hope you understood, right? So don't worry. And another message to you, to all the aspirants is I yes I know, I know this course this syllabus I have to follow here is basically the BSc standard. But you think yes, I followed the BSc syllabus, but you know one thing, I give you the lectures in some one or two level I give you the some standard level. I give you lectures some one or two level standards. I mean in equivalent to MSc levels. Okay, equivalent to is MSc levels. So don't worry about that. Is it sufficient or not? Is it useful for your future examinations like JEST or GATE or CS and NET? Don't worry about that. Yes, okay, yes, I know. This is the part. This is the syllabus for BSc semester 4, but I tried, but I give you some standards, some advanced level. So I give you advanced preparations also. Okay, not give you just like a university level preparations. Just you go through all the theory and give the semester exam. Not exactly like that. I give you some trick also, and I give you some standard approach also. How can you deal the competitive exam questions? So this all kind of features is actually I covered here. Okay. 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 And so what is the complex variables actually here? Complex variables. So complex variable, let's say a complex number. Let's say complex number, that is omega equals to f of z. So here a function of complex number. So here basically w is nothing but a function of a complex number, and the variable z is a sometime called z is nothing but complex number. So here, so when a function uh, when a function w is a function of a complex number, that is called, and the variable is basically complex number here, right? So here omega is a function of complex variable, complex number z, right? Okay, it's okay. Next I come to here the single valued function and multi-valued functions or many valued functions. I try to cover here. What is single valued functions? Okay, uh, let's try to discuss the what is single valued functions. Okay, it is very important. You know, so single valued functions, what is the meaning of this single valued function in complex variable? Single valued function in complex variable. Okay, basically here in a complex analysis, a function is called single valued if for each complex number the functions give you only one unique value. Okay, let's say f of z, w equals to f of z is a complex is a function. Okay, and for each value of z, let's say z equals to z1, z2 and z3, for f of z1 gives you one value, single values, f of z2 another single value, and f of z3 gives you another single values, right? So basically then this function is called uh, single valued functions. Okay, okay, understood. So in complex analysis, a function is called single valued if for each complex number z, the functions gives only one unique value. Okay, one unique value, that is very very important. Okay, one unique value. Okay, understood. So let's say some example of single valued functions. So first example is basically the polynomial functions. Okay, the polynomial functions. So like f of z is equals to an z to the power n plus an z plus a0 z to the power 0. So this kind of polynomial functions, or for an example like f of z is equals to z cube minus 2z plus 5. Okay, f of z equals to z cube minus 2z plus 5. Okay, so for each z values is unique, because I mean for each z values we get unique f of z values for this polynomial functions. Okay, so this is the example of the single valued functions. Let's say another example. That is rotational functions. I mean not rotational, rational functions. Okay, rational functions. I hope you already know what is the meaning of these rational functions. Like f of z can be written as like p of z upon q of z in this poem. So for an example, basically written as f of z is equals to, let's say, z plus 1 upon z square plus 1. So this is one kind of example of a rational number. So for each z values, here also we get a single one unique values actually for different z values. Okay, so this rational functions is defined everywhere except where denominator is 0 basically. Just remember one things, a rational functions, complex functions, okay, defined everywhere except where denominator is 0. ठीक है, जहाँ पे डिनोमिनेटर 0 होगा ना उसमें उस जेड वैल्यू में एक्चुअली इस फंक्शन को तुम डिफाइन नहीं कर सकते, मतलब उस वैल्यू में उसका फॉर दैट डिफाइन नहीं कर सकते हो तुम इस नंबर को. ठीक है, तब इसको तुम सिंगल वैल्यूड फंक्शन नहीं बोल सकोगे. अंडरस्टूड? So this is the another example of single valued functions. Okay, let's say another example of like exponential functions. exponential functions. Okay, so we already know exponential functions written as basically to the power z, right? So this function is a single valued, obviously single valued. Second properties is uh, it is basically periodic in imaginary directions. Yes, this functions is periodic in imaginary directions. Imaginary directions. Okay, so this is another example of single valued functions for each z values. Okay, you can get only one values. Like another are the basically trigonometric functions, hyperbolic functions, all that. Trigonometric functions like sin z, cos z, tan z. These all are like, for an example, let's say sin z equals to, here basically sin z is equals to e to the power iz minus e to the power iz upon 2i. Also let's say cos z, that is equals to e to the power iz plus e to the power minus iz upon 2. So these all are basically the single valued functions. Okay, these are the single valued functions. And 5 is basically hyperbolic functions. Already you know about that. Hyperbolic functions like sin hyperbolic z, cos hyperbolic z, tan hyperbolic z. So these all are the single valued functions. Okay, and one thing you remember, the power functions, integer power, but very very important here, power functions, but it should be integer functions. Should be integer functions. Okay, that means f of z equals to z to the power n, but where n should be integer. Okay, so f of z equals z to the power n is a single third function, but z to the power 1 by n is a multivalued functions, because we discuss about that, because z to the power 1 by n is multivalued functions. Or discuss about that, why it is called multivalued functions, or discuss, don't worry, it's called multivalued functions. Okay, so this is the one example. 7 is the principal logarithmic. Again, it is mensual. Principal logarithm after branch cut, that is very very important. What is branch cut? We also discuss. The functions called principal logarithm after branch cut, that is log z equals to ln r plus I theta with minus pi to plus pi. In this restricted argument, restricting argument, this log jet is called basically single valued function. So these are the some single valued functions. Okay, these are the some single valued functions I list here. So please focus about that. Indeed, we already discussed about what is the power functions, why z to the power 1 minus n is called multivalued functions, and why log z equals to NLR I theta exactly called single valued functions after branch cut. Why it is not called multivalued functions, we discuss in later actually. Okay, I understood. I think you understood. Okay, nice. So very good. So this is some example of basically single valued functions here. Okay. Okay, very good. In the next lectures, I discuss about multivalued functions in details, and also branch cut and branch point. These are the very important topic. Okay, good. Thank you, and please subscribe and share this video with your friends. Thank you, and keep learning and stay healthy. Okay, thank you.